This video is going to go through the steps on how we solve pH problems with weak acids and weak bases. So the other day in class, you learned how to calculate the pH of a strong acid or base. So just as a review, if you want to find pH of a strong acid or base, all you are going to do is the negative log of the hydrogen ion concentration or hydronium ion concentration if you want to get pH. And if you want to get pOH, you're going to do the negative log of the hydroxide ion concentration. That's it. You don't do anything else. So, if you want to find the pH of a weak acid or base, you're going to have to do something different. Okay, so what we want to do is we want to think about what's the difference between a strong acid or base and a weak acid or base. Well, if you remember, we have talked about this kind of over and over again. And a strong acid or base completely dissociates. So what that means is you get 100% ions. Okay, and sorry about my writing there, but so strong acids or bases completely dissociate, so you get 100% ions. So all of the solution is composed of the ions. But in the case of a weak acid or base, it only partially dissociates. And so we talked about how with strong acids or bases, it's kind of like a stoichiometry problem, and weak acids or bases, it's kind of like an equilibrium problem. So let me write an example of each. So let's take a weak acid. So something easy, hydrogen cyanide. And we've got that dissolved in water. So we will get some proton or hydronium ion and some cyanide ion. And because this is an acid producing hydrogen ion, we are going to have a Ka that's going to be less than 1. In the case of strong acids or bases, the Ka or the Kb are so large that they're immeasurable. I don't even know if immeasurable is a word or not, but anyway, they're too big to measure. So we don't even have to worry about a Ka or a Kb. In the case of a weak base, so let's think of like maybe ammonia, and we're going to put that with water. When we write reactions for weak acids, we can either use water as a part of the reaction or not use water as a part of the reaction. But when we're writing it for weak bases, we're going to have to include water because the proton is going to have to come from somewhere. So here we're going to get hydronium, and then we're going to get hydroxide ion. So we know that ammonia is a weak base because it produces hydroxide ion. This is equilibrium because it only partially dissociates. So we have some ions, but we have much more of the molecular ammonia. And because of that, our Kb is less than 1. So the equilibrium is shifted to the left. Same thing with the reaction with the acid. The equilibrium is shifted to the left. We have much more of the molecular cyanic acid than we do of the ions. Okay, so what we're going to have to do when we have weak acids or bases is these are going to be equilibrium problems. So if you think back to what we did before break, With these, you are going to have to set up an ice chart. So you cannot just jump to negative log of the hydrogen ion or hydroxide ion concentrations, because the concentration of your weak acid or base is not the same as your concentration of proton or your concentration of hydroxide ion. So that will not work. Okay, the other thing that you're going to need to know to do these problems, and this is in the case of a weak base, is there is going to be a relationship between the weak base and its conjugate acid. So, for instance, let's look at you can really do it either way. I'm going to take ammonia because that's the one that I wrote before. We've got ammonia in water, and ammonia will accept a proton from water, so it's going to form ammonium and the hydroxide ion. Now, there will be a Kb for ammonia, and we can look that up in the table in the back of the book. I think it's on page 1116, and I will find that the Kb for ammonia is 1.8 times 10 to the negative fifth. Now, if I look at this reaction, ammonia is our base because it was a proton acceptor, and that would make ammonium our conjugate acid. Now, there's a relationship between these two. So, if we take 1 times 10 to the negative 14th, which is Kw, that is equal to Ka times Kb. And if you are interested in knowing how that's derived, you can look that up in your book, or tell me, and I'll make another video that's going to show you that. But for right now, this is the relationship that I want you to know. So if I decided to reverse this reaction, or for some reason I was going to need to reverse the reaction, and I had ammonium plus water, and ammonium is an acid, and that's going to donate a proton to water, so I'd get ammonia and I'd get hydronium. So I would know that ammonium was my proton donor, so that's my acid. Ammonia would be my conjugate base, and because hydronium is produced, I know I would have a Ka, but I don't know what that Ka is. I can use the Kb for ammonia because my conjugate acid-base pair is ammonia and ammonium. And so there's a relationship between the two, and that relationship is that the Ka times the Kb will give us 1.0 times 10 to the negative 14th for that conjugate acid-base pair. So if I want to find the Ka for ammonia, I'm just going to use, for ammonium, I'm just going to use this relationship. So I'm going to rearrange it. I know what the Kb is, but I don't know the Ka, so I want to solve for the Ka. That is equal to 1 times 10 to the negative 14th divided by the Kb. So 1 times 10 to the negative 14th divided by the Kb for ammonia, which is 1.8 times 10 to the negative fifth. So when I solve, I get I'm going to do sig figs, 5.6 times 10 to the negative 10th. And what this is the Ka for ammonium. So it works both ways. You'll need this to be able to do some of the weak acid, weak base problems.